So we have Rami Jreige here today from the University of Bristol to talk to us about dark matter detection.
Yeah, so thank you both for inviting me here. It's nice to be back. And yeah, this is kind of part of the work I was doing that's a continuation from really the talk I gave in September here. Because every time I present it, the contrast with LIGO and LHC comes up, or someone asks a question either about, hacking's extragalactic reality, or, the experimental's regress. So I decided to kind of push this idea even further and just make it mainly about the contrast with LIGO and LHC and kind of see, is there something specific about astrophysical or cosmological experiments, or can we draw kind of comparisons with other types of modern experiments? So I'll start by kind of briefly explaining DMEs, dark matter experiment setups, just the general idea of them. Then I'll have a brief discussion or a bit more in depth about observation versus experiment, kind of the hacking idea. And most people agree that astrophysics and cosmology has observation, not experiments. But at the same time, I think that's not the main idea. The experiment is just a way, it's kind of like an epistemological channel, right? More than anything. And once you put it in that kind of terms, the contrast with LIGO becomes kind of more prominent with multi-messenger astrophysics. And of course, the contrast with the LHC, specifically the Higgs boson discovery, is very interesting because they're both looking at particles with unknown masses. So kind of, we're trying to figure out how to constrain the parameter space and finally see if we get detection. So they've been running for decades, dark matter detection experiments, but we have no results. We have lots of results, but we don't know how to interpret them. We've neither verified nor falsified, which is a weird situation to be in generally. And the problem is usually interpretation. The difficulty is epistemological, where the initial conditions are models. They're educated guess at best. And there's also a theoretical underdetermination that's specifically in that article by Wolf and Reed, where the idea is that dark matter is just, there's a certain amount of mass in the galaxy. Besides that, there's not much information. It could be really a bunch of different things, primordial black holes, WIMPs, even matchers at some point were tossed around. And there's also an experimental underdetermination in the interpretation. So every time we try to force interpretation, we get a degeneracy. And in this talk, I'm just going to make a contrast mainly with LIGO and a bit with LHC to kind of highlight, really show them more philosophical in the more philosophical light. So this is pretty much what I've been banging on about. They've been running for decades and they function with similar principles. You choose a target material. This is from Xenon 1T. They use xenon for electron scattering. You put it in a vat, you shield it as much as possible to make sure there's no external interference. Shield it even more by burying it deep on the ground. So you have the one in Gran Sasso in Italy, the most famous one. You have one in South Dakota in America. You have many right now around the world. There's more than a dozen, I think, right now. And then you wait. And you hope to get something like the infamous Dama Libra results, right? So I say infamous because there's lots of controversy. So I'm not going to go into it, but kind of the idea is that you're expecting not just hits, but something of an annual modulation signal. And the reason for that.
Can I ask something about this experiment?
Yeah.
So in a container, what is supposed to happen inside the container? Is something being done or?
No, you wait.
No, you just wait.
Because you're expecting a certain distribution of the dark matter in the galaxy. Yeah. So sooner or later, they're going to hit us. And when they hit us, they'll hit one of these arrays. And then you get energy. You get a photon detector that just detects a hit.
You just wait.
Pretty much. I mean, this is over 25 years. This is the number of days. Okay. So this is around 9,000 days with a bit of a gap to move to phase 2. And so this is me trying to get ChatGPT to give me a picture. It failed miserably. This is the best one I could get, just to let you know. I really don't think this is what the solar system looked like. But the reason you get the modulation signal is because we're assuming to be going in a dark matter wind, right? So as the Earth goes around the sun, sometimes it's going into the wind. So you have the WIMPs approaching us at high velocity. You get more hits. And sometimes you're going away from the wind in the same direction, so they have less energy when they arrive. So we get less detections. So it's sinusoidal over the year.
We now get ether vibes.
Exactly.
Yeah, I was saying, yeah.
It's exactly the same idea. It's exactly like ether. Because if the sun's moving in the galaxy and there's a wind, well, a uniform distribution, because that's another assumption, then this is what you should look like. Now, the reason Dama Libra is infamous is because they were not being able to be recreated. We don't have the data anymore. They've stopped releasing it. And the problem of interpretation really shows up when you look at the two experiments that tried to reproduce it, Cosine 100 in South Korea and Anais in Spain. They both got null results. It was not reproduced. However, the detector response is the problem. So from the 2024 review of particle physics, they mentioned that the results from the 173 kilogram per year exposure in the 1 to 6 keV energy range are consistent at 68.3 confidence level with both the null hypothesis and Dama Libra. A larger exposure and a reduced energy threshold are required to test Dama Libra for 3 sigma. And the problem with the reduced energy threshold is that we get more noise, and noise elimination becomes more difficult. So essentially, you need to test it at the lower end of the mass range, because the way Cosine and Anais tested, even though they both use sodium iodide, technically we could still find a way to save it.
Perhaps a little bit tangential, but in particle physics, you want 5 sigma, and
Yeah.
astrophysics, we don't really have a convention. Is it more like particle physics or more like astronomy?
This is
What would constitute discovery?
no one knows. I think that's kind of the whole thing of dark matter.
Mhm.
Do we have detection? No one knows. Has it been falsified? No one knows. The thing is that maybe because we have so few information, let's start with 3 sigma, I would say. Right. I think that's the idea. From my understanding of, it's a review of particle physics, right?
Yeah.
But from my understanding is that start somewhere. Because right now, even with Dama Libra, Anais, and Cosine, we can't even hit 3 sigma. So what I presented here last time in September, and I'll get back to it later a bit, is that we have a circularity in the result interpretation. Right? The detectors themselves are based on just non-relativistic quantum mechanics scattering, right? But we assume the existence of dark matter because of GR and lambda CDM. So there's a disconnect between the two. In the experiment, there's no assumption of GR. If lambda CDM is wrong, even GR is wrong, the interpretation of the experimental results technically are unaffected, which is quite different from LIGO at HC. So there is no theory relatedness. So to put it differently, anytime, yeah, tell me.
So why did you say it follows they will be unaffected?
So
that something's not T-related doesn't mean it has no consequences.
What do you mean? I'm not saying it has no consequences for GR lambda CDM. I'm saying that the interactions in the detector are non-relativistic quantum mechanics. So whether CDM exists or not, whether GR is true or not, the interpretation of the results technically should still be the same. Right? So in LIGO with the interferometers, nothing from QFT can cause a change in the interferometer signal. Right? In LHC, nothing from non-particle physics can cause the results we get. In this case, they're independent. Because we're just basing off of scattering, which has nothing to do with GR, unless we want to go into quantum gravity, but that's a whole other beast.
Could you also elaborate a bit on this first point?
Yeah.
Because if an experimentator has a detector, then the detector registers something or it does not. And how can this be based on non-relativistic QM?
Yeah, I'm getting to a bit with the contrast, but the short answer is simply that how can you tell what's noise? How can you tell whether you have a genuine detection or noise? That's the problem. So with LIGO, one of the issues that Jamie Elder points out and a couple of others is that you can tell when a signal is genuine because it confirms GR. GR tells us how it should look like. but you cannot tell whether a signal it falsifies GR because you assume everything else is noise. In this case, the problem is that how do you tell what's noise, what's not? Right. So one of the ways they do it, for example, in Xenon 1T specifically, is that if one array gets a detection, they consider it as a noise. If you get two simultaneous detection, that's a true signal. But that's just Xenon 1T. Every different experiment has different noise filtering. So noise is the problem. And the more you reduce the sensitivity threshold, the more sensitive you make it, the more susceptible it is to noise, which makes it difficult to filter out noise. And this becomes a problem. So if you look at the interpretation, the results, the circularity that I'm mentioning, any attempts to force interpretation means either we completely rely on particle physics and interpret everything as noise, because particle physics tells us nothing can cause this that deep underground. So essentially, we're just going in circularity. We're showing particle physics is true because we're assuming it's true because everything is noise. Or we assume the data from the experimental results is genuine, so forcing them to be interpreted as dark matter or some dark matter candidate. Because otherwise, we have no way to interpret the data. It makes no sense if we've tried every possible means to eliminate all particle physics interactions. So some of the data sometimes are interpreted as dark energy by some, or as solar axioms. But all of this is just as much guesswork as calling them WIMPs. There really is no way to discern. And this is why here, it's like, so in September, I went to technical details. Here, I'm just going to compare it as observation experiments, because we can go to technical details and I can show from the physics side how there's a mass degeneracy in the result interpretation. However, once we start comparing it to LIGO and LHC, that's when we start seeing some kind of a lot more philosophically interesting issues pop out, right? So famously, in extragalactic realities, Hacking says in astronomy, we just have observation. So our science is truncated because we just have models and we have too many of them at every possible layer. And the transition to natural science in the 17th century mentions is essentially a transition to the experimental method, right? So we kind of, it's not saving the phenomena, but creating phenomena, like interfering with nature, forcing something to come out. And even Jamie Elder in a 2024 paper calls that astrophysics an observational science. The empirical evidence rely on are observations of naturally occurring phenomena, which, I mean, I don't disagree with it, but I think the whole manipulation, experimentation kind of hides what we actually are looking for. Because the question is, what's the importance of manipulation, of creating the phenomena, right? Mm-hmm. So in Jamie Elder's paper on direct versus indirect observation, she mentions Colin's interview with one of the scientists from LIGO, where he says that the difference is that the Taylor crowd, a previous gravitational wave detection experiment based on some electromagnetic radiation, observed a gravitational wave transmitter and figured out how it worked. We figured out how to build a sufficiently sensitive gravitational wave receiver, and since we built it, we know exactly how it works. Those words in italics, as Colin, represents a huge advance for gravitational wave physics. So this kind of idea that manipulation and creation gives you deeper access to the knowledge of the model, gives you a better idea of whether the truth of the model. So we get a better knowledge of what's going on. Does this imply knowledge of the phenomena? So this I go back to a previous article of mine where I separate into a taxonomy of models, but here I'm just going to focus on two. So the phenomenological model, which is a model of the phenomena itself.
Sorry, quickly, if we go back to
how
what do you mean when you say how it works? Is that I thought, so one slide back, I thought that didn't have anything to do with necessarily manipulation, but then you paraphrase it as something to do with manipulation, right? You can have an instrument right? I can know exactly how my telescope works without thinking telescope has anything to do with manipulation. Right? I can know all the correlations between different parts of the instruments.
Yeah.
Right?
Absolutely.
But you're saying, you're interpreting them as saying.
Yeah, because I'm getting there specifically to contrast it with hacking, because hacking talks about, where is it? Creating phenomena, right? So I'm basing it mainly on the creation, because even hacking doesn't say manipulation. Hacking says creating phenomena, right? And it's rare to see people saying manipulation. Maybe it's the wrong word I use or too early. People talk about creating phenomena, contrast to saving it. And here they talk about create. Since we built it or we created it, we know how it works.
Yeah, but you didn't create the phenomenon.
No, but that's where I'm going with this, is that the whole point is that we have a phenomenological model of the phenomena and we have the experimental model of the experimental setup.
Mm-hmm.
So in LIGO, because they created it, they have the experimental model 100%. They don't have to. So the whole point was that with the previous Taylor crowd, they'd never created the setup. They were piggybacking off of some electromagnetic receiver. So they had to kind of try to understand how the receiver works for a while before they can start interpreting results as gravitational waves astrophysics. Here, they never had to do it.
Yeah.
And that creates an interesting contrast with controlled experiments versus just observation in astrophysics, right? Because so if we take the phenomenological model as the model of dark matter distribution in the galaxy, so the particle mass, velocity, area, and then you have the experimental model is of the experimental setup itself, so the materials in the vat, and that changes between experimental setup. Models of the interaction that take place in the detector, so in this case, just scattering, nothing to do with GR. Then what we're looking at is that hacking is talking about manipulating or creating the phenomena, is experimentation, right? Having sufficient knowledge of the phenomenological model. And the responses is usually about, we have experiment in astroparticle physics, but it's manipulation of the experimental setups, right? So the knowledge we have is slightly different in how it appears. For hacking, what he's saying is that we don't have sufficient knowledge of the phenomena that we're looking at because we can't control it. We can't create it. We can't interfere with it. And a lot of the times when you look at kind of astroparticle physics or even philosophy of astroparticle physics responses or something along similar lines, it's always about manipulation of the experimental setups. So it has to do with understanding deeply the experimental model and thereby recreating the phenomena or saving the phenomena. So the whole point I want to say is that what's important in this case is not the actual manipulation or experimentation, it's the epistemology, right? Because manipulation is an epistemological tool. So if we reframe the debate in terms of epistemology, how much do we know about the phenomenological model versus how much we're assuming? And then we ask a more interesting question which shows up with LIGO in a second. Are there means by which we can enrich our knowledge about the phenomenological models? Then we're asking a different question. Then experiment specifically manipulation or creation doesn't matter as much. What matters is how much can we ground the knowledge that we have? I don't mean it in metaphysical grounding. I'm not a big fan of that word. Actually, so this, kind of just to put in context, this program lends itself well to a Bayesian understanding of experiment, to kind of a Bayesian analysis, which is something me and Karim might start doing soon. But as of now, I'm just going to leave it as kind of more robust, less robust, without kind of going into too much details. So the contrast with LIGO then. LIGO detects the gravitation. LIGO or LIGO?
I say LIGO, but I don't know.
There we go. LIGO detects gravitational waves from astrophysical events, right? So binary black holes or neutron star mergers. And GR provides the templates for the waveforms. So detection is done by match filtering the data with the theoretical waveforms. So Elder points out that this introduces a circularity. We use GR-based models to identify signals that then just confirm GR's predictions. So LIGO mitigates this by performing various consistency checks. Right? So they change the phases of the two detectors and see whether anything matches up or not. I mean, this is all in Elder's work, right? I don't know much about it more than just what I've read in her papers. But the interesting thing about it is that this just confirms GR, right? There's no way for LIGO to violate or falsify GR because most other signals are interpreted as noise.
Is there some part of the story where she says, if you subtract from what you think is the signal the noise, and that's the residuals are not white noise, then you know there must be some extra signal in the noise, so you can know it's in kind of theory neutral way.
To a certain extent, yes, but even that is limited. So I was recently at a talk. I've been looking for the paper. I don't think it's out yet, where they were looking at non-waveform templates analysis. So what was it called? I forgot what was the name. Exploratory, kind of like unrestricted exploration of gravitational waves.
Yeah.
And the problem they're having is they cannot tell what's noise, what's not.
Yeah.
Right? If you leave it unrestricted and you're not specifically looking for a specific template, it's very hard to tell what's noise, what's not, because the interferometers have to be so precise that you just don't know what's noise.
No, but I thought what Elder was saying, even if you do use a template, and maybe you need one, then when you use a template to figure out what you think is a signal, and then the remainder is noise, in those residuals you can do some statistical checks, and if the residuals have weird correlations in them, there's not this random white noise, you can say, oh well, this noise doesn't look like noise, there must be some signal in there which my template has picked out, so at least I know there's something other than my template. I have no clue what it is.
Interesting. I don't remember that. Maybe I have to go back and read it, because it's interesting to see it and compare it, especially now how it's going on with the kind of since the detection of the of GW78017 since whatever they've opened it up to see if they can get kind of unrestricted, and I've seen some talks about it and they just don't know.
No.
They're facing similar problems to dark matter detection actually, where you just don't know what's noise. Also not to mention, of course, LIGO Event Horizon, they're all over the world now. So it's the difference between opening up just one or just having a whole collection. But what makes it interesting here is when we start talking about multi-messenger astrophysics, right? So multi-messenger astrophysics is the comparison of independent lines of evidence. So for example, signals from different sources. So electromagnetic radiation and gravitational waves, right? If we get from the same source two different signals, we can compare them and contrast them, find out they have the same source. And that means we have a more robust understanding of what's going on, right? We're no longer relying just on unknown gravitational waves. And Elder in the paper points out that the 2017 LIGO detection of GW, this number, was the first to join detection of gravitational electromagnetic radiation from a single source, as well as the first, and so far only, multi-messenger observation to include gravitational waves. So she calls this the consilience kind of argument, where the idea is that for the same source, you get two different lines of independent evidence, each pointing to the same conclusion. So in theory, you could say that just from the gravitational waves, we know that this was the binary neutron stars, but we also have gravitational waves. But we also have the electromagnetic signals that we got from them, and we got for them simultaneously. And of course, electromagnetic detection is much more robust. We know the interactions very well. They're not based on something that we haven't seen before. So multi-messenger astrophysics increases the robustness of the phenomenological model. And as she puts it, robustness is a property of a hypothesis or claim. An hypothesis has this property to the extent that the evidence supporting it is varied, such as it is independent in the sense described above. So I'm not going to enter the whole robustness debate, which is just a soup and a mess. So I'm just relying on Jamie's definition. I'm more than happy with it. That's why I said I'm leaving it open for now, because we're moving more towards a Bayesian analysis of it to kind of give a bit more formalized epistemology approach to it. But we can just put it very simply, we're just more assured of it. Epistemologically, we know that these models are verified properly. So we can have a bit of a deeper, kind of a bit more trust in them. And then we can say via the gravitational waves, we know they exist now. So can we use such a thing for dark matter detection experiments? And why or why not? Well, the problem with dark matter detection is that it's a status quo. There's no events to give us dark matter. Right? It's just uniformly distributed. It's kind of like trying to detect the gravitational wave from the sun. There's no lines of there's no independent lines of evidence for dark. I mean, the whole point is that there's no electromagnetic interaction, so that's out of the way. But there's no events going on, right? The only events that lead us to believe in dark matter and dark matter's existence is galactic formation, inflation, and cosmology, which, you know, now we're in the cosmology realm. We've gone past astrophysics. So, well, it's just very simply, there are no events. There's nothing to uniquely characterize dark matter in the way that you can do it with LIGO. There's nothing to say that, you know, gravitational waves are indicative of some event, of something. There is nothing to do that with dark matter. They're just there. And this points to really the first difference, is that LIGO itself uses general relativity for the experimental model, right? And the phenomenological model for both. The interaction of the interferometers is via gravitational waves. And the events that we see kind of send out gravitational waves, right? And in the phenomenological model, you have events, which gives you variation. So when you're waiting for something, you're waiting for something specific. You're not just waiting for the same thing to happen, like the status quo to just pass. You're waiting for an event. But we don't have such wiggle room for dark matter detection. There's no events that could possibly tell us something's right, something's wrong, like the filtering you were talking about earlier that Jamie Elder mentions. That doesn't work for dark matter detection because there's no events. In theory, it's supposed to be consistent, or a modulation signal, or if no modulation signal, a consistent signal of some sort. Mass will. What was I trying to say? Mass will or should be specific. Okay, forget this. I don't know what I wrote here. I missed a couple of words probably. So the whole point is that the experimental model is particle physics, has nothing to do with GR. And particle physics has no need for the existence of dark matter, right? So no events, nothing within the experimental setup itself that is based on lambda, CDM, or GR. So there can be no multi-messenger astrophysics for dark matter detection. There can be no way to filter out a specific signal of a specific event in a specific way. We're just looking at the background noise, essentially, and trying to filter out the background noise. Because we're trying to detect a particle, right? In the modern physics landscape, there's no way to force a GR explanation for detection interaction like LIGO. So if we get a signal in LIGO, we know it's not noise. We know it's going to be a gravitational wave. If we get a signal in one of the detectors and we know it's not noise, we don't necessarily have to look towards astrophysics for an explanation. We could get one from particle physics somehow, or at least not even dark matter, right? Some of the candidates for Xenon 1T events have been dark energy. So there's no unique characterization, no waveform template within the detectors. Now, the contrast with LHC, the discovery of the Higgs boson, specifically with Franklin's work, is the other side of the coin. Because as Franklin points out, the mass of the Higgs was not predicted by theory. And because the production cross-section and width vary wildly across the allowed mass region, CMS had to be flexible. And this is the idea we also see with a lot of the dark matter detection setups. They have to be flexible. They have to allow for a relatively big mass range, but not too big as to become too indiscernible. The key difference, however, is there has been numerous. Is there a pointer? Yes. Doesn't work.
Yeah,
right.
the screen absorbs it.
Yeah, I figured. So there's been numerous previous searches for the boson, and the mass region excluded 95% confidence level by Atlas was all these various results. This is not possible for dark matter. As we saw already with the DAMA, the null hypothesis and DAMA are both consistent to 68% confidence level. Here you have mass region excluded at 95% confidence level. That's just not possible for dark matter. So why is it the case? So Franklin points out that the first step in the analysis was to identify the particles and to reconstruct their trajectory and to measure their momentum, energy, and angles. There was also a calibration procedure for the experiment. During the past several years, the CMS has replicated much of the history of 20th century particle physics. This procedure demonstrated the ability of the apparatus and the analysis procedures to produce correct results and provide support for the credibility of other results obtained by collaboration. This, I would say, really is the difference between kind of astrophysics or astroparticle physics experiments and particle physics. There's no way to calibrate dark matter detection experiments. There's no way to test it against anything else. There's nothing to recreate. There's no way to verify that your analysis, your noise filtering techniques are correct. You can't even, there's no way to identify particles or reconstruct trajectories because, in theory, assuming WIMPs and they're just weakly interacting, all we're going to get is just energy. So this kind of places a big gap there because dark matter experiments face the same kind of problems as originally looking at the Higgs boson with a massive weight range. But the difference is that there's no way to exclude anything from here. There's no calibration. So we can't control. There's no previous result to recreate. There's nothing to recreate. Which kind of points out that really it's not astrophysical experimentation like LIGO. It's a cosmological experiment. Because our main lines of evidence, the events we have, are just really cosmological events. We have no astrophysical events that can point to dark matter. It's just kind of a bit of a background, something that exists in the background, like the CMB, for example. At least in our current understanding. Right? The only thing we can know is that the scattering, if it exists, will produce energy. So the dark matter experiments, they have energy thresholds, but they can't discriminate. So they have a minimum energy threshold. Anything above that energy, so anything going with a higher velocity, is just going to give you a hit. But there's no way for you to discriminate because the mass is unknown, the velocity is unknown. And this has led to a WIMP mass degeneracy, where essentially if all you have is a certain energy threshold, then from there you cannot recreate either the mass or the velocity. There's always a way to theoretically work around it to show that the same event can be triggered by a high mass, low velocity or low velocity, high mass particle. And there's not much theoretical data to go on, right? Particle physics as we know it fails without the Higgs. Right? The results of the experiments, both the phenomenological and experimental models need to be reanalyzed and reinterpreted for the LHC. That's not the case with dark matter. Only cosmological models will undergo change. Experimental model remains intact. So there's no way to kind of recreate or even at the failure level, reanalyze. Which means the big key here is that you can't falsify. This is a key issue. You cannot falsify that a specific dark matter of a general weight range doesn't exist because the experimental setup's unaffected. So what do we have to go on then? Kind of wrap up at the end. So we have a lot of indirect evidence of dark matter, a lot. And we keep discovering more and more. But nothing tells us anything except mass exists at some level, somehow spread out. There is no certainty that there's particles or any particle candidates. Could be primordial black holes. Superfluid has been also, people also talk about MOND. There's many different candidates. And there's also persistent underdetermination of astrophysical phenomena. So Wolf, Reed, and what's the name of the third author? Sorry. Wolf Italia point out that there's a persistent undetermination. So what we see macroscopically that points us to dark matter can have various diverse explanations on the micro-physical level. And there's really no mechanism to pick out which one's the correct one. And there's no events we can wait for. Nothing that can provide a strong signal all of a sudden that will tell us, we found something. So from the phenomenological model, we have a lack of knowledge of initial conditions. We have a lack of multi-messenger astrophysics because there's no events unique to dark matter that would point in that direction. And from the experimental model, there's an underdetermination of the detector results, because any hits we get, any results we get, we can reinterpret them as something different. So determination also is on the detector level, which causes a degeneracy in the WIMP mass, or any particle for that matter, unless we can use unique particle physics characterizations, which so far we can't. So, to summarize, the problem of interpretation is just a problem of uniqueness in both the identity of the particle as an object and its interactions. It does not provide any unique interactions. It does not provide it. We cannot characterize it uniquely in any form or fashion. So it's a problem of uniqueness, first and foremost. Thank you.